Thank you very much, Philip, for the introduction. Good morning, ladies and gentlemen. Thank you also for the opportunity to speak today. In the next 15 minutes or so, I'd like to give an insight into opportunities for federated analytics in low voltage electricity networks. This is an area where we've been active in applied research at the Lucerne University of Applied Sciences and Arts. And we think there's a lot of potential for applying federated learning and federated analytics in low voltage networks. So it's definitely an area to watch. Before I start, I'd just like to introduce the Digital Energy and Electric Power Research Group at Lucerne University of Applied Sciences and Arts. As it says on the slide, we deliver applied research projects relating to design, operation and maintenance of power systems. We combine traditional power systems knowledge with knowledge in advanced analytics. As a field for research, this combination of expertise, I think, creates a really interesting intersection of themes, allowing us to bring together some of the traditional power systems disciplines, things like power flow analysis and asset management and planning and design, with emerging topics in data science and our experience in hardware and also in communications. Means we're actually able to extend that knowledge into edge applications and IoT. So that makes it really interesting. So what would I like to cover in today's presentation? First, I'd like to give a short introduction to federated learning. Then I'd like to cover federated learning in the context of LV networks, focusing on an ongoing research project that we've got called Knowledge that's been funded by the Swiss Federal Office of Energy. So using that project as a reference, I'd like to look at the setting for federated learning in low voltage networks, low voltage electricity networks, and to talk about what I see as the DSOs or the utility in relation to the application of privacy preserving AI. So introduction first. So what do we mean by federated learning and how is it applied to power systems, especially in low voltage networks? So as some of you will be aware, federated learning is a machine learning approach that allows learning to take place at a location where the data is generated. So the approach basically splits the training process up across multiple nodes rather than relying on the centralization of data. And this splitting up, this federation provides two main benefits. Firstly, it inherently protects privacy by removing the need to centralize data. And secondly, it helps reduce the volume of data that must be centralized for analysis to take place. So if we consider a power systems example, there might be load curves coming from individual households, and the traditional approach would be for utility to collect all of those in a master database, typically in a head-end system that forms part of the advanced meter infrastructure. So in practice, this creates problems for the utility. In reality, in order for them to be able to do anything other than analysis for billing purposes, the utility needs special permission from the customer, as load curves in particular are seen as sensitive data and are highly protected by regulation and by privacy laws. And the other issue for the utility relates to the volume of data that can be transferred versus the volume of data that's potentially available through the metering infrastructure. So typically load curves are mapped at 15-minute intervals and transmitted to the utility once a day. However, it's possible to generate data at a much higher resolution without adding much complexity to the meter design. So federated learning helps alleviate both of these problems by allowing learning to take place at the place where the data is generated at the meter. So this helps the utility address their privacy issues firstly, and then secondly, it helps address the volume issue as well. So how does it work in practice? Well, a server will initiate a request to a node to start a training process on a model that's either transmitted to the node or exists already on the node. On receiving the instruction to train, the node then carries out a limited training process on its own local data set. And the data set's normally small and the model training is only partial and it's based on a limited number of iterations. And then after the required number of training epochs, the partially retrained model is sent back by each node to the server. And then each server combines the models into an updated federated model. And the updated model is then delivered back to the edge devices and the process can continue. And so in this way, each device contributes to training without transferring sensitive data away from the source. And with only an updated model being sent back, the amount of data being exchanged in theory is significantly reduced. And so in this way, federated learning provides an opportunity both to reduce the volume of data that's transmitted and also to address some of the privacy concerns around utility data such as load curves. So what else do we need to consider? So I've talked about volume, I've talked about privacy, I've talked about regulation. The second aspect to consider is difference in behavior from node to node. And this is another interesting aspect in relation to power systems. So federated learning works well when one node produces a subset of data that may not be properly reflected in a global model, as the individual behavior of that node might be masked by a large volume of data. So federated learning allows differences in nodes to be captured in the training process, and so could lead to better performance overall. The type of model is important. So federated learning can only be applied if there's some meaningful way of combining the models. For example, by averaging weights or gradients or intersects, applied to linear models or, for example, aspects of neural networks. However, if the underlying model relies on shapes that can't be averaged, things like decision trees or forests, then combination isn't possible using this approach, and so federated learning can't be applied. So that concludes the introduction. I'd now like to look a little bit more at the potential applications in low voltage power networks. And I've tried to summarize some of the potential use cases on this slide. So in our current research project, we're looking in particular at smart meter data. And this is the use case in the middle of the slide here where we forecast household consumption. Forecasting is also possible in other areas. So for example, for electric vehicles. So there's potential for federated approaches to be used to characterize driver behavior, for example, or predict vehicle charging patterns or monitor states of charge for allowing vehicle to grid applications and so on. So local learning would allow user behavioral patterns to be understood without relying on transferring that information to the utility or revealing information to the utility. There are also cases related to distributed generation. So federated learning could apply to embedded renewable energy forecasting, where computation and forecasting is done on IoT sensors at the grid edge. We're currently working on another project that's funded by InnoSwiss that's looking at this area. And predictive maintenance is another one, just looking at the top left of the slide. This is a well-publicized use case for machine learning in general. For example, things like predicting remaining useful life, but also applying to local diagnosis of faults or sharing models between plants without compromising privacy is also possible. And then finally, when we look at the LV network, there's potential to distribute the computation to nodes, helping to alleviate privacy and data transfer issues. And it's that last one that I'd like to look at in a little bit more detail in the context of the project that we're working on at the moment. So this project has been funded by the Swiss Federal Office of Energy, and we're working with Swiss utility Romand Energy, with smart meter manufacturer Landis+Gyr, and with a federated learning solution provider via Science. And we're working on a number of different use cases that are of particular interest to Romand Energy. In this project, the primary data source is the residential smart meter and mostly the load curve that comes from that. So in the first two cases shown on the slide, we use data from smart meters to better understand network congestion, and then we run a machine learning-based algorithm in use case 2 to predict future demand profiles. And so we're able to identify where congestion is likely to occur. In the third and fourth use cases, we're planning to take readings from smart meters to provide better insight into power quality issues by combining smart meter readings with readings from other devices across the low voltage network. And finally, in the last use case, we're investigating how load curves can be used to profile customer behavior and to use this information to offer dynamic tariffs or to support dynamic tariffs for Romand Energy's customers. The different use cases are being developed to different levels of detail and to different levels of maturity in the project. So for the detection of congestion and the prediction of congestion, we plan to implement field trials in a test field in Roll. This is a test field with around 700 smart meters, phaser measurement units, and also advanced grid monitoring units that are provided by DEPSIS that monitor low voltage substations. For detecting quality of supply issues, we're going to conduct very much more limited field trials. And then for predicting quality of supply issues and applying local tariffs, we're just carrying out an academic literature review in this particular case. A central problem here, or a central question, is about hardware and the hardware capabilities of individual smart meters are critical in the success of this particular use case. Now, the details, the hardware capabilities are commercially sensitive because of the competitive situation in the market. And so because of this, we've defined categories of hardware requirements using anonymized information from various sources. And I've shown those on the slide. So the low specs column here probably corresponds with today's standard smart meter, residential smart meter. On the other end of the spectrum, we're aware that some smart meter manufacturers have started looking into Linux-based operating systems, but we believe that this high-spec category isn't sufficiently cost competitive at the moment to be applied in residential smart meters. Having said that, the medium specifications is a reasonable configuration, we believe, for the next generation of smart meter. And so we're using this as the basis for prototyping federated learning in the Knowledge project. One of the big unknowns here is whether we can successfully run learning on this configuration. So embedded hardware for training at the edge is largely unproven. A lot of work's been done on mobile phones, which have a lot of processing capacity and storage. However, when you look at embedded devices, for example, the hardware configurations that are typically on a smart meter, the existing body of research is much more limited. And this really presents a challenge for us as a University of Applied Sciences, because we're trying to bring novel approaches that have been developed in academia into production for commercialization. So that link to production is absolutely critical. So if we focus on that prediction use case, I just wanted to explain briefly the approach that we're taking and how federated learning fits into the process. So to predict congestion, we're actually combining a number of different algorithms into a single workflow. So the basis for this is a distributed power flow calculation, which avoids centralization of smart meter data by instructing smart meters to exchange readings with each other. This allows the utility to build up a power flow calculation for the low voltage network based on the backwards forward sweep without centralization of that data. So that's a distributed computation approach that's applied there. For prediction of congestion, we apply some algorithmic complexity to the process, which is shown in green. So we're developing an ML-based prediction algorithm for smart meters that allows them to forecast the load curve at a point in future that's interesting to the DSO. And in this way, the DSO is then able to run the power flow calculation and the result will be returned to them. So where does federated learning fit into the picture? It doesn't fit in everywhere. So some of this is distributed computation and some of it we hope will involve federated learning. When we've got the stable prediction model on the device, we're able to update that periodically using federated approach. And then the prediction model can be updated based on stored local load profiles, allowing the prediction to improve over time without the centralization of data. And although we're developing our prediction model in TensorFlow, like those of you who are paying attention would have noticed the obvious flaw here, we're still unclear about which framework we'll use to run the federation process. Will that be TensorFlow federated? Still not sure at the moment. We're investigating various options. The maturity of the tooling and the frameworks that are available for federated learning is an issue. And encryption and security is a particular problem that we need to address in the use cases that we're investigating in this project. Just more or less a final slide here. So commercial tools are emerging that allow data scientists to combine some of these open source frameworks for managing the federated workflows with security protocols that protect the integrity of the process and preserve privacy. And in the project, the focus of the project is not on developing these privacy-preserving protocols themselves. It's more focused on applying the federated learning process. So within the project really adds a lot of value here. So they're providing a capability within the project. They provide an enabling environment called TAC, federated workflows, that we apply to the project. And that controls what the user can do with the workflow by controlling user access to data and controls who can run which query on which data set and at what period of time. And this environment TAC also ensures consumer privacy with a range of computational elements that can be applied to an execution contract to protect sensitive data. So there's a range of techniques that can be applied to this. So in this way, we're able to, in the project, to combine the best of open source federated frameworks with a robust system for managing security and privacy of data. And hopefully that will close the gap in this, the capability gap in the existing tooling. So that brings me to the end of the presentation. It's got a high-level overview, and it's a big topic, so it's difficult to cover all of the important aspects in a lot of detail in only sort of 15 minutes or so. But in summary, so I've given you an introduction to federated learning, and I've described how it can be applied to low-voltage networks. The main takeaways that I'd like to highlight: first, this is an area where I see huge opportunity in the electricity sector. Second, device capabilities are increasing, but there's still a lot of research risk here. We're able to do more and more on the smart meters and the microcontrollers, and we think we can put together the building blocks, but there's still a lot of unknown. And thirdly, there's still a lot of research risk here. So if people are looking at working on applying federated learning and advanced analytics to low voltage network and low voltage data, my recommendation would be to work with a University of Applied Science with experience in this area, if you're thinking of exploring further. So on that note, pleased to discuss new collaborations, and also very pleased to answer any questions that people might have.
Great. Thanks a lot, Ben, for this very interesting talk. Was very interested. So the session is now open for questions. As usual, the process takes a bit of time to be established. So let me start with the first suggestion. You mentioned before that many of the building blocks are already available. You also mentioned the huge potential of federated analytics as a technology. So the question would be, what is the missing link? Or as you put it, where could University of Applied Science help to kind of improve the speed of the adoption of federated learning in the market? So where do you see the first required steps?
I think that where University of Applied Sciences adds a lot of value is it's got that connection between industry and theory. And the approach that we're trying to take in the Knowledge Project really takes advantage of that. So we're starting off with smart meters being a very constrained piece of hardware. And we're trying to work back from that towards the theory of federated learning. So we're firstly looking at a distributed computation approach. Then we're looking at how we can improve models using federated learning. And then we're looking at optimization and cryptography and those aspects there. So I really feel as though that link to the meter manufacturers, that link to the real world use cases, that link to the data is where University of Applied Sciences can add value. It can be a little bit different where if you start with a very theoretical approach where you're looking at the, if you like, vanilla federated approaches, and you try to apply those to a real world system. I think that the approach we're taking hopefully will mean that we end up with some sort of hybrid solution that is still exploitable by a utility, that still can be applied by a smart meter manufacturer, that still can be adopted in the real world in some way.
Cool. Thanks a lot. We have time for one short last question. So Max Corell is asking, previously sensitive information can potentially leak through the model itself. This means the model learning the specific examples. Do you apply some kind of differential privacy to make sure that this does not happen? So how can you make sure that there is no leaky pipeline?
Yeah, and this is a couple of years of projects, and we can't solve all the problems within the project itself. And that's the question of privacy, the question of encryption, the question of making sure that the consumer data is protected. This is where the partner VIA comes in. So they've got a company with a mature enabling environment, and they offer things like differential privacy, homomorphic encryption. They also offer k-anonymity and sanity checks, a range of different tools. And we're able to, I mean, it's not as simple as this, but we're able to take those off the shelf, if you like, from VIA's toolkits, and we're able to apply them. So we're able to focus in this project on the exploitation of data and providing value to the utility. And then we're able to take those, if you like, commercially mature tools and apply them to the problem to make sure that the cryptography and the encryption problem is dealt with. Otherwise, the scope of the project would just be too large. So having them as a partner really has helped us focus on the particular use cases and areas of interest that are the focus of Rwanda Energy.